Hey Bob, have you heard of gizmos? We've got to make hundreds of gizmos. They're the latest thing. They're going like crazy. We'll make a fortune.
Slow down a bit, Mark. We've never made a gizmo before. Do we know how many we need and what size they are? What's it going to be used for? Are the regulations we ought to be meeting? Do we have a requirement? That's the critical question for any system. Do we have the requirement? Here is an example of a need. I want something to get my clothes clean at a price I can afford. Now you may think the customer is looking for a washing machine, but there are other options. If your customer is on the road or staying in a hotel, then a laundrette or laundry service may be the best solution. Again, if they're isolated 100 miles from anywhere in the wilderness, a stream and a flat stone may be the only option. And even if a washing machine is what the customer wants, there are questions to be answered. And it's in answering these questions that we're starting to build hard facts, even hard numbers, which the product design team can use as a starting point for the design. And that is the beginning of building up the requirements for it.
There is a sophisticated process going on here, and we've not seen it covered well anywhere else, including, I regret to say, our own lectures. The need and the purpose, and a further step, the objectives, are all different but interconnected things, and the fundamental success of the final system will depend on how clearly thought through these steps are. As Bob said, the need is the problem or desire that the customer has. In Bob's example, the need statement is, I want something to keep my clothes clean at a price I can afford. The need statement should be short, a single sentence, and focused on one need. If there are several needs that could be met by one solution, then you should reword the need statement until you have embraced these several needs into one need. Now, to fulfill this need to clean clothes, I have decided to acquire a clothes cleaning system with the purpose to clean clothes automatically. It may sound the same, but notice I've already made choices about how the need will be resolved by defining the type of system that will be developed. If I go to the shop with just the need, am I asking them to clean the clothes, or asking them for advice on how to clean clothes, or asking for a washing machine? The purpose makes it clear I am asking for a washing machine. It sets the direction for the system solution. Again, it should be a single sentence statement, and it is the purpose that is the foundation of the system development from there on. I think perhaps the difference between a need and a purpose can be more clearly seen in the start of the American Apollo Moon program. In early 1961, President Kennedy suffered the political humiliation of the failed Bay of Pigs invasion of Cuba, on top of the Soviet Union launching a man into orbit. This was a sensitive subject because criticising the rocket technology gap between America and Russia had been a key point in his election campaign. So his need was to have a spectacular political move to bolster his weakening position. As a consequence, on the 25th of May 1961, he presented NASA with a goal that was effectively a system purpose statement. He asked NASA to land a man on the moon and return him safely to Earth before the end of the decade. This was a very clear purpose, and it was highly measurable. And of course it was met by the Apollo 11 landing. But of course the need that led to it had long since evaporated, which in part explains why the American space program drifted so badly after Apollo had completed its purpose.
It's interesting that the military tend to have rather good system engineering processes, but as a consequence often have trouble with large-scale projects as their need changes as the world situation changes. And this reflects back to the requirements late in the project life cycle. Well, Mark, you've explained the difference between a need statement and a purpose statement, and I think we're agreed there, although it's very rare for a project to have both formally defined. It's nevertheless a good idea to have both. But what are these objectives that you were talking about? How do they differ from the purpose?
Well, Bob, the problem with the purpose is that it can be rather vague. It may mean something to the customer, but may not mean so much to the people who are going to be asked to build the system. So when NASA was told to go to the moon, that was very clear and understandable. But to clean my clothes automatically is not really enough for a design team to get on with designing that system. They need more information. So because it's too vague to be explained the purpose, we have to expand it with objectives such as these. These things are measurable and understandable to both the customer and the outside world. Here are some possible objectives for the washing machine example. Note that they are designed to give the team who will be doing the requirement generation later the ability to ask the questions that lead to requirements matching the purpose. You should not have too many objectives, 5 at the most, and they need to be something that is understandable to the customer and also something that is measurable. It is these objectives that should be the key technical input into the requirement generation activity that will be undertaken in the funded developed project. And they have 2 functions. Firstly, they are the starting point for generating requirements. And secondly, by measuring the system as it develops against these objectives, we have a direct assessment of whether the system is genuinely going to meet the need, a process technically known as validation. Here's an example from a project that I'm currently working on. This is the Scorpion. It is a concept design for a nuclear-powered spacecraft capable of transporting people and cargo from low Earth orbit to the Moon and beyond to Mars and Venus. I've been working on it for over 6 years, so I must have a need. And here is the need statement. Now there's some unusual aspects here, the real biggie being I need the design, not the actual built spacecraft. Although if someone with a spare $40 billion did want to make me one, let me make it clear I am not going to say no. So I am looking for something that will be readily understandable, be exciting, be inspirational, and hence have an impact on the debate about where humanity should go in space. I had a choice of many possible systems, maybe a new launch vehicle, or a lunar base, or a Martian base, a giant space station, but in the end I selected a transport spacecraft as the best way to meet my need. Hence this purpose statement, which is guided by the goals of NASA's post-Apollo program, which was never undertaken, but would have culminated in human exploration of Mars. And while this purpose is clear, it's also a little vague, and it may be possible to meet this with a design that doesn't really quite hit my need. Indeed, there are an unnumbered multitude of system and infrastructure proposals that purport to meet this purpose. So we need the objectives, the things that expand the purpose with the detail to ensure that it will genuinely meet the need. Now here, the first objective makes it clear that I need it to be a single vehicle. And when combined with the second objective, it means that that vehicle needs to be able to land on the Moon. And that's the Scorpion's unique selling point that makes it stand out and grabs people's attention. And bear in mind that that's what the need is about. That is grabbing people's attention. So why specifically exclude landing on Mars or Venus, which would have been even more attention grabbing? Well, they're not included because of the third objective. I'd done enough work to realise that using technology we have or could have now would mean a single vehicle from low Earth orbit to the Martian surface and back was just simply not possible. This shows that this process of exploring a need and deriving the system's objectives to meet it You should be doing a lot of technical and cost feasibility work to ensure what is being asked for is achievable and at a cost that is affordable. The next stage is to start a funded development project to produce the system, and even the first requirement generation phase of the system lifecycle is going to cost tens of millions. And you do not want to be spending that sort of money only to find out that the required system is not possible when that could have been established while the objectives were being set. Hopefully, you will be starting to understand that a lot of work needs to be undertaken before a development project can be started with its own system lifecycle. Where that work is done varies from organisation to organisation. When it is done by the customers with the need, like space agencies or defence organisations, they will be conducting concept studies or feasibility studies exploring the organisation's needs. If it is done by the system manufacturer, they will have marketing studies or future studies to try and identify their customers' needs so they will have a product ready to meet it. Either way, the function of these studies, that often cost hundreds of thousands to millions, pick your own currency, should be to firstly identify the need and encapsulate it in a needs statement and establish the options that are available to meet it. Secondly, to select an option and encapsulate that option into a system purpose statement. And thirdly, to amplify the purpose into measurable objectives that can form the input to start a proper funded project. Now, when you get into the big wide world, are you going to find everyone going through this cycle? Sorry, no. Very unlikely. And you will also find that the terms need, purpose and objective are often mixed up and confused.
Well, Mark, you say we get confused between these different things very readily, and I would perhaps ask a question that will be going through people's head as to why do we need all this detail for what in the end will be a few lines on a piece of paper that defines all these different things.
Yes, and of course in doing things like using examples like washing machines, where you wouldn't use these processes anyway, you sometimes don't see the need, which is really apparent when we get to these very large projects doing very complex things. The essence of doing this is to get the focus right. So when you start the project off, there's a very clear understanding about the need you're meeting and the way you're going to meet it. And although we're only talking about ending up with 5 objectives and 2 statements, there should be an enormous ton of paperwork leading to the justification for those things.
And I think in part it's that we're now talking about teams which are more than one person. When it's all in one person's head, it doesn't matter. But when we've got multiple people, again, on large projects, not even necessarily in the same company, then we've got something we can point to when we debate, is this really what we're supposed to be doing?
Yeah, I mean, for example, back in the day when we were doing those studies for ESA on European space stations in the 80s, there were, 4 companies involved? Yes. We all had 3-4 people in each company working on it. The problem is I don't think we were working hard enough on need, purpose and objectives. We were just having fun looking at what a European space station would look, possibilities, and not focusing it down into something. I mean, none of those studies came up with something that you could really move forward and develop a European space station on. Bob, can you recall a feasibility study that gave the project a firm, clear, definable, measurable set of objectives?
I'm afraid not. And I agree that history shows that this is likely to cause problems later. Although it may not be perfect, these early concept studies, which are funded from general budgets, are the starting point for system development projects which are separately funded in their own right, and which will follow the system life cycle we outlined in the previous video. And the first phase is requirement generation, so we need to address what requirements are. The goal of the requirements generation phase is to find and document all the specific properties that the system must have to meet its objectives, preferably in the form of definite, quantifiable statements we call requirements. The need, purpose and objectives will be short statements of intent, lacking in detail. The requirements must tie this down by being precise, unambiguous and complete. We develop requirements by asking questions about the need and purpose in light of the objectives, and also by thinking about such things as where the system is going to operate, what it's going to interface with, and whether there is, for example, a legal regime that demands certain things of the system, perhaps to be considered safe to operate. In this, we start to recognise, even though the requirements represent an agreement between customer and supplier, that other people and agencies, we'll call them stakeholders, have a part in it.
Bob just introduced an important piece of terminology there, so perhaps we should explain what a stakeholder is. We've talked about a customer, that is the person who has the need and is buying the system. But having defined a purpose, the system will impact people other than the customer. And the customer and these other people are collectively known as stakeholders. That is, everyone who will be affected by the system if it is built and operated, and therefore will have potential requirements on the system. In setting the objectives of the project, the focus will be on the customer's need. In this requirement generation phase of the project, the examination will need to extend wider to the consequences of meeting that need and the impact on the wider community. We've also talked about the supplier, that is the person or organisation that actually takes the customer's money and hands over the system. But with a large system, there is a much wider community involved, and all those people and organisations are collectively known as players. Here are some examples showing stakeholders and players in different contexts. And another one, for example, would be the railways. I use a train every now and then, but I'm not involved in buying a train. But yet I have requirements on the train, so I am a stakeholder in the railway system. And on the player's side, there can be some unexpected organisations involved. For example, entire countries. Look how much effort a government will put in to obtaining a large systems order because of the impact on society and the economy of the wider country. If you follow the definition of stakeholders to its logical conclusion, everyone on planet Earth is a stakeholder in every system. But since it's not very practical to consult everybody on every project, some limits must be placed on which stakeholders are involved in requirements generation. But in fact, the requirements from society at large are encoded in laws, and these form part of the system's constraints. So there is, in fact, a process for everyone to have their stake recognised and involved. Having explained stakeholders and players, let's return to Bob, who has an example.
Let us look at a more high-tech example, a communication satellite. What the customer wants is something that transmits a television signal down to a particular area on the surface of the Earth at a cost that allows them to make a profit. What we want to know more precisely are what frequency you're going to transmit at, what signal strength do you need on the ground, what area you're trying to cover, we call this a footprint, and are there limits on signal strength on adjacent areas, will the neighbours complain? And in the absence of a detailed business plan, how much money do you have allocated for this satellite? Note that each of these has numerical answers, and in most cases they're either maximum or minimum values. These questions create the requirements. In some cases it might be useful to feed comments or possible solutions back to the customer to get a better idea of what they really want. But eventually it is the quantitative requirement on the right hand side which will form the basis of the eventual contract. An important point about each requirement is it must be verifiable, so that in due course we can prove that the system we've built meets those requirements and thus fulfills the contract. Almost all the requirements in a real large project will be technical, but technical requirements come in several types, and we need to understand each of them. Functional requirements state in quantitative terms what the system should do. I'm going to talk about these in detail in the next lecture, but they're inherent in achieving the purpose of the system. Interface requirements define the agreed connection between our system and the outside world. They make life easier for us by removing our responsibility for things outside our control and by defining the boundaries of our system. They can include such things as dimensional constraints, where does it fit, power supply assumptions, communications interfaces with the outside world, how do you switch it on and sometimes more importantly switch it off, and waste disposal assumptions. Environmental requirements define the conditions under which the system is required to operate and may include also transportation and storage environments. The environmental requirements can get quite extensive and are often separated out into a separate document, so the same document can be used, for example, to define the requirements on subsystems at a lower level later. Operational requirements form a hold-all that includes such things as design lifetime, reliability, fault tolerance, and such things as mandatory safety design factors and margins. Indeed, almost anything which has not been covered somewhere else. And finally, we have verification requirements. Because some of the requirements are not always easy to establish by direct measurement, for example, will the spacecraft operate successfully on the surface of Mars, we need to agree what is a satisfactory demonstration that the system can perform what was called for. These can include calibrated analyses, where we do a limited number of tests, but then use computer simulation to confirm that the system will work over a complete range. We even sometimes verify by heritage. This has worked in this environment every time we've used it in the past, and so we expect it to work in the future. The important thing is the requirements should be demonstrable, and then we must establish what constitutes an adequate demonstration. We should notice that each of the requirements, with one exception, form absolute constraints. They present limits which must be met, and in doing so carve off half the universe of possibilities. In this scheme of things, there are no soft constraints, things that it would be nice to have, but which we could do without. So how do we deal with the things that it would be nice to have? I said earlier that there's one exception to this rule, and that is something I'm going to call performance. I'm using performance here as a technical term with a very precise definition. If you have two system designs, each of which meet all the requirement constraints, then performance is that single factor which determines that one design is better than another. Sometimes performance will be easy to identify. It may be the price, or payload delivered, or size, or some other factor. But more generally, it will be more complicated. It covers all those nice-to-have features which we excluded from the rest of the body of the requirements. Note that it's perfectly possible to have an absolute constraint on one parameter. The mass has absolutely got to be less than this. And then add an additional nice-to-have. It would be nice if it were lighter. But it's necessary that it should be just a single performance parameter. Otherwise, it's easy to get into arguments in favour of one option against another. We will have a later lecture devoted to establishing performance in these cases. But properly, performance should be defined within the requirements, and soft requirements eliminated. Unfortunately, very often this is not done, and as a consequence, unresolvable arguments can plague the later project. Establishing and agreeing requirements at the start of a project is a critical step in system engineering, and changing requirements later, or not being clear at the outset, remains the biggest single cause of cost overruns and other problems. TBDs, to be determined, in a requirement document means that we do not know then what we want, and an unknown cost is coming to haunt us later. Sometimes we use fast prototypes or simulations to establish exactly what the customer is looking for. And this is particularly true when human-machine interfaces must be established. And we use feasibility studies to discover what the possibilities are and what might be available if we just relax this or that requirement a little. But effort taken to create a good requirements document, and sometimes to challenge the underlying assumptions, represents a saving for later when we have to commit large sums of money to the project.
Well, Bob, at the end of the requirement generation phase, the key output, there are others, but the key output is something that's normally called a requirement specification. When we were discussing the script for this video, you had a problem with using the word specification.
Yes, to some extent. When I get a new piece of kit and the user manual with it, and on the back page it has something called specification. And the specification is a very definite implementation of something that meets the requirements, which I don't even see. The requirements doesn't tell you what the design has to be to meet that requirement.
No.
It doesn't
being
specify
specific. It is being specific about these are the specific requirements. I think the key here is we shouldn't focus on the word specification.
Yes.
There's lots of types of specification. There's the specification, the product specification you've mentioned. Yeah. There are design specifications, which is where you specify what the design will be, normally in answer to a requirement specification.
Yes.
So it's the first word that matters, not the second.
It's the first word that matters, and equally according to requirements document, or something of that nature.
But normally the word is requirement.
The specification, in this respect, tends to be banded around generally, and I don't think it's got much of a meaning in that respect.
No, but I'm sorry to disagree with you. I think requirement spec is very clear, and everyone would understand. If you, it's like letters. If a letter, what does it mean? If I say it's a love letter or a contract letter or a final demand letter, they're all very different things. They're all letters in one respect, but you wouldn't write one the same as you would write another, and you wouldn't expect them to have the same sort of import. So, when you're in industry, you'll almost certainly see these documents called requirement specifications, but be aware there are other things called specifications, and they really are quite different. So, we have these system requirement documents, also called system requirement specifications. And what they do is list all of the stakeholder requirements that have been identified in the requirement generation phase. We would suggest that the purpose and the objectives are included in the introductory text to this document. They're not part of the requirements, but they do give them a context. Now, this is very rarely done in real life, partly because it's so rare to get a well-defined purpose statement and the corresponding objectives, but if you do have them, we definitely would recommend putting them in, as it preserves the project's inputs and disseminates them widely for the later stages of the project. And when the project reaches this stage, that necessary reminder is there to help. After the introductory section, we list the requirements. So what should a requirement look like? Well, here are the 9 requirements for a requirement. Okay, let us start with the wording. A requirement should be expressed as a concise short paragraph, and it should be worded in the future tense, but using shall, not will. The use of shall is a subtle point. For a start, it is the correct wording from a legal point of view. And remember that the requirement specification is often part of a legal contract. But the main reason for doing it really is that if you do not write a specification using shall, it looks unprofessional. It looks as if you've not been trained to write specifications. The second point is to use paragraph numbering. So each requirement has a unique number and can be easily referred to during work on the project that's going to happen thereafter. The next point is to ensure that each requirement statement only has one requirement in it. Sometimes a statement ends up effectively asking for 2 things, especially if you follow our later advice about keeping requirement specification as short as possible. In trying to make them concise, this mixing of requirements can happen. The fourth point is saying do not specify the technical solution, only what is needed. This is sometimes difficult for engineers writing specifications because, of course, they have an opinion on how the requirement should be met, particularly if they have a feasibility design that they have generated to test the requirement's viability. But that temptation must be resisted. It unnecessarily constrains the system design team, who will be doing a much more detailed and comprehensive job on the system design to find the best solution. The next point is just concisely state the requirement and do not include any exploration or other flumbuffery in the requirement itself. Now, this does not stop you adding an explanatory commentary, and we'll be coming to that later in the video. Number 6 is never state what you don't want, only what you do want. In other words, do not include negative requirements as in the system shall not. So that means actually I should have worded this particular point as only include positive requirements. The next point is to avoid duplicating and conflicting requirements. Now this may sound sort of obvious, but as requirements are built up by a team or making their own contribution, this is a surprisingly common problem in real life. Number 8 is to express requirements as a minimum that is acceptable. The temptation is to just put a number in that you want, but this means the system has to meet that number precisely, and this is often difficult and expensive to meet. So express the requirement as greater than or less than, showing the area of flexibility. So if you want a car that goes as fast as a car is allowed to go on British roads, you should specify the top speed of the car shall be greater than 70 miles an hour. But if you want to also avoid the temptation of really excessive speed, you could specify the top speed of the car shall be between 70 and 100 miles an hour. It's part of making sure that requirements express only what is needed and nothing more. And finally, you should express requirements in a measurable way so that they can be verified. That is objectively proven that they have been met. Now that normally, but not always, means hard numbers that can be established by testing.
Once we have the requirement document, or if you want the requirement specification, then what does it do? Well, there are 3 key functions. First, it is the technical input to the system design team, who, in the next phase, will be the team charged with the development. It provides the reference document for starting the design, giving us numbers that we can use, establishing the agreed interfaces with other systems, and later, as we produce possible designs, it serves as a check on the validity of the design and how far we've progressed towards achieving a complete proposal. Because it's a physical record and not something carried around in the designer's head, it can be shared among members of the team, and later can be used as the basis for subsystem design requirements as we partition parts of the design to our subcontractors. And because it must address the question of how do we prove our design works, it eventually defines the test and qualification process at the very end of the project before it's delivered to the customer. In many cases, the requirement specification is owned by the customer paying for the development, and the design will be owned by the supplier, so it serves as an interface between customer and supplier. In cases when a system is made by a supplier for several customers, then it's the supplier's marketing and sales departments who will be acting as surrogate customers. Either way, it should be assumed that this is the sole technical communication between 2 separate teams of engineers. Which brings up the second function. The requirements are either dictated by the customer or agreed between the customer and supplier, and then form the basis of the legal contract between them. So that later, when relationships break down and one side is suing the other, and the customer says, "That's not what I asked for," we can go in front of the judge and say, "Look, we can prove that the system delivers this much, and in size it's less than that much," and we can go through everything in the requirement line by line and show that we've delivered everything that was asked for, or if the customer, that they have not. And that highlights the third function of the requirement document. In the introductory video, when we define the concept of the system as a set, we emphasise that the system boundary is defined in words. And to be precise enough to make sure the customer ends up with a system they need, it may take a lot of words. So where are these words that define a system boundary? Well, they're here in the requirement specification. In other words, the requirements, as defined at the end of the requirements generation phase, defines the system. Now, for all these functions, the requirements work best if they're kept to a minimum. Every added requirement increases the cost and the risk that we will not be able to achieve it in the end. There is some tendency to write requirements documents with hundreds or even thousands of pages. If it is a major project, the thinking goes, then the requirements need to be spelled out in detail. But a better practice would be to put effort into seeing what the absolute necessary requirements are. A document hundreds of pages long will not be used, or if it is, will employ hundreds of staff continuously checking that the requirements have been met. Simple requirements will work wonders in later stages of the project when thousands of people are trying to coordinate their efforts to bring the system into being.
I do have a particularly ripe example of how not to do it. It was a customer-produced requirement specification for a certain communication satellite, which I will be discreet enough not to name. And British Aerospace was competitively bidding to build it. The actual specification was over 130 pages, and while we know of much longer specifications, it is still way too long, and it was completely full of unnecessary requirements. The real customer requirements were along the lines of the communication satellite example Bob used earlier. And with that in mind, let's look what it said about launching the satellite. To set this into context, the requirement was for the supplier, that is British Aerospace, to deliver the satellite to its operating geostationary orbit, and that means the launch system is inside the system boundary. It has no system interfaces and therefore should not be the concern of the customer's requirement specification. If we could have got Captain Kirk to use the Enterprise's transporter to beam the satellite into its orbit, that is the same as far as the customer is concerned as whether we use Ariane or Delta rockets. Nevertheless, the requirement specification listed the launchers that we could use, and it was a reasonably comprehensive list of the smaller launches that were available at the time. But it took away the option of buying a slightly larger, more expensive launch system and making a cheaper, heavier satellite. Okay, so that wasn't good. But then they set the requirement on the maximum mass of the satellite. It was almost as if they didn't trust us to be able to read the launch system user manuals, which define the maximum weights. And in reality, they were different from launcher to launcher, not just the single value defined in the specification. And they need to be different as the propellant needed by the satellite itself was different depending on where the launch site was located. So not only was there no need to specify the maximum mass, they did it in a way that actually hindered and constrained the design unnecessarily. But then they went further and then went on to specify the dry mass of the satellite and hence the propellant load and hence by implication what propulsion technology we should be using. Well, in the end, British Aerospace won the contract. But when the spacecraft were actually built, they did not meet either the total or the dry mass specifications, nor were they launched on exactly the launch system specified. Did any of that matter? Well, if I can be permitted a little bit of boasting, 2 of the 4 that were built hold first and second places in the longest ever mission lives for geostationary spacecraft, and all 4 exceeded their mission specification by a large margin. It not only shows that they were well designed and built, but that they were providing the service the customer wanted. In short, they were meeting his needs for decades, despite not meeting his specification. And that means the specification had things in it that they didn't need. While we're on the subject of keeping requirement specifications as small as possible, I remember there was a conference in the mid-80s in Huntsville, Alabama, where you gave a paper that really was the paper of the conference. Do you remember it?
Well, we were arguing that it's a motto that I keep, which is every requirement adds to cost. Remember that, every requirement adds to cost. And therefore you should keep the requirements to the absolute minimum that you need.
Yeah.
And ideally, particularly in the early days, a lot of very good projects run on requirements which didn't last more than a page.
Yeah. So your argument, if I think the paper title was one-page specification, one-page requirement specifications, and it went down very well. And I remember at the end of the conference chair pointed to Ernst Schulinger, the electric
grand old man,
the grand old man, ex von Braun, of course. Yeah. And he said to Ernst, Ernst, I seem to remember that the V2 specification was on a single sheet of A4. And Ernst just sort of looked and puzzled for a moment. No. It was on half a sheet.
Yes.
Well, a single sheet of paper requirement specification may be a little difficult in the modern world, but we would still offer it as an aspiration. The half-page specification of the V2 rocket was typical of the period. Remember, these are small projects, and that in part is characterised by minimal specifications. Here is the Ministry of Aircraft production specification for the Miles 52, an experimental aircraft that was intended to break the sound barrier. It never did, because the project was cancelled in 1946 before the construction of the aircraft was complete, and the reasons for that cancellation have never been fully established, despite at least 2 books on the subject. Now, if it looks to you a little like the Bell X-1, in which Chuck Yeager did break the sound barrier in 1947, it's worth remembering that Bell Aircraft had copies of all Miles's research and design information while they were developing the X-1. Now, using the rules for requirements we established earlier, there are clearly things to criticise here, like unnecessary requirements. Why does the all-up weight actually matter? You may also be thinking that requirements 1 and 5 look suspiciously like technical solutions, and indeed they are. But is that wrong in this case? The Miles 52's purpose is technology research, so in this case it's sensible to specify the technology that you want researched. These very short specifications with around 5 requirements have the characteristics of what we are calling objectives, and they do make more sense in this light, that is, as inputs to a project before it's funded. What didn't happen in these small projects is the formal requirement generation phase of the system life cycle thereafter. While emphasising that the requirement specification should be as short as possible, this can lead not so much to problems but missed opportunities. If the only technical information that crosses the customer-supplier interface are the requirements, the supplier can miss the bigger picture. And given that the suppliers are likely to be the experts in what is being asked for, they're probably going to have a valuable input as to how to best meet the real objectives. So although the customer will get what he asks for, he may be missing out on something better. Boeing realised that this was actually a serious problem and kicked off what they called the Working Together Initiative. They got all their supplier contractors together, and the Boeing CEO then explained that the problem was that the suppliers were giving them what they asked for, not what they wanted. And if this was happening, then in large part the problem must be with the requirement specifications that Boeing was giving their suppliers. Their solution was to add a commentary to the requirement specification. The requirements themselves follow the basic principles that we've already outlined, but each requirement then has a commentary explaining why it's being asked for. You can see the principle in this example of a specification for a space docking standard. The commentary is in italics. Now, this worked in practice as is illustrated by a story I heard from GE Aviation in Cheltenham. They were asked by Boeing to bid for the undercarriage control electronics for the Boeing 777. The specification asked for a rather dumb electronic box that would take the data signals and turn them into control commands for the undercarriage. Because they had the commentary, GE Aviation understood what Boeing was after, and they gave them a quote for the dumb box, but pointed out they also had an off-the-shelf intelligent command unit that could do the job, even if it did not strictly meet the specification, and it would save Boeing a lot of money. Boeing had not realised units like this existed, and when they understood what it could do, they started putting them in other places on the aircraft. So it's a win-win all round. GE sell more units, and as there's no development risk, they make more profit. Boeing reduced the cost of the aircraft, and the customer gets a better performing product. So in normal circumstances, we would strongly recommend including this sort of commentary in requirements documents. Well, Bob, I think we're going to have to address the somewhat difficult subject of things called user requirement specs, because it's possible that people might come across them. But before we get into discussing the spawns of Satan, I think perhaps I should explain the concept. The idea of the user requirement specification is that this document frames the requirements in a way that is understandable to the customer using their terminology and jargon. And then this user requirement specification is translated into a second technical requirement specification, which uses the terminology and the jargon understood by the supplier. The idea is that the customers will have a better understanding of what they're getting, and therefore something more likely to meet their real need. So the single interface between the customer and supplier of just the requirement specification becomes a chain, with the translation between the user and the technical at the centre of this chain. Well, Bob, what's your opinion on these?
It's putting a problem in that explains why a lot of things that the general public buy on computers do not work as expected.
And it is a concept that's particularly used by the computing industry.
And it is particularly from the computer industry. I've noticed you put user requirement specification in there. I half expect you to say user requirements, which means that the person who uses this has to follow these particular requirements in order to be able to use the machine. Yeah. Best machines provide a understandable interface with the people who will use it through actually understanding how human beings behave. Yeah. What we've got here is we've got a number of people whose job is to translate from one language to another.
Yeah.
And that's probably not the best way of ever doing anything.
I mean, we've got several problems. One is the translation's never going to be perfect, so you've introduced another error in the system. And the thing that always struck me when I was first introduced to the concept is, which one is the legal document? Which is the one that is actually defining the system?
Oh, precisely, yes.
Yeah. So when you're up before the judge,
that's right. Could I go through this and say we've met that, we've met that, we've met that?
Yes, and then I'll bring up the other document and say, but did you meet that?
Yes, exactly. It's the problem of traceability that requirements should set down the initial thing, and everything that follows from that has to say this comes from requirement 1.32.
Yeah. Yeah, absolutely. And I think the core of the problem is the labelling, because people have talked about technical requirement specifications, and therefore said, well, then we have a user one. And requirements don't have to be technical. I mean, in most industries, most of the requirements are technical. But there can be other requirements, and the requirement specification should have captured all the requirements, whether they're technical or legal or aesthetic. Now, for example, the Rolls-Royce I'm going to buy on my commission from your excellent book will have technical requirements, like how many people it can carry, how fast it can go, but it will have a legal requirement that I want it to obey British legislation so I can drive it on British roads. And it's going to have an aesthetic requirement that it will be in blue and gold because those are my heraldic livery colours. So, I think if you just keep to the word requirement specification and just the one, you should be all right.
Yes, it's always the problem about linking from one thing to another.
Yeah.
That happens there. We do occasionally get into slight differences because of the way jobs are done. In scientific spacecraft, for instance, then there will be a requirement for the spacecraft, but there will also be a requirement for the instrumentation, the payload, the science package. And that's because the science package is evolving in parallel with the spacecraft. So it defines how, so effectively there's an interface between the two, and that's what we're really defining, that this thing will work this way according to this interface, and this payload will fit on my spacecraft when we've decided what it is.
Yeah. And a final point on these and why we don't like them is in the next lecture we're going to be dealing with functional analysis. And I can't think of anything that's going to mess up a functional analysis more than trying to stick a user and a technical requirements thread in that breakdown. But we anticipate in the next video. A final word on requirement specifications. I was teaching a course, actually rather similar to this one, on our systems engineering doctorate programme, about a decade ago. And it was given to people who had come from industries that were using systems engineering, which is why their employers were funding this expensive training. After the requirements lecture, I set as a sort of homework to find the system requirement document for the project that you are working on. And about half of them couldn't find it. So for all our theorising, do not expect the real world to match the ideals that we have laid out in this video. It raises the question, why couldn't they find these requirements documents? Well, I suspect in some cases that's because they didn't exist, which is rather worrying for the project. And in other cases because it was being hidden from the lower ranks, which is also worrying for the project. The key point at the heart of using system engineering in large projects is that the whole team have a common understanding of the system that they are working on. And the key document that can provide that common understanding is the system requirement specification. So it should be available to the whole team. And if it has followed the advice of this video, it should be readable and understandable and hence hopefully read and understood. Well, that concludes our video lecture on requirements, and we have hopefully impressed upon you how important requirement generation is to the subsequent success of a system development program. In the next video, we will be looking at the process of deriving requirements through a technique called functional analysis.